We have a sequence of random variables which are R-valued xn and a constant c. And we were asked to show that xn converges to c weakly, that is, in distribution, if and only if it converges to c in probability. The if part actually follows from a corollary in the notes for general x. All we have to do is set x equal to c. But we could also prove it directly, using the idea that convergence is equivalent to every arbitrary subsequence having a sub-subsequence that converges to the same limit. So we have to start with a subsequence, which we call xnk. That's a subsequence of the xn. And since xn converges in probability to c, we know that xnk does as well. And then from a result in the notes, we know that convergence in probability implies a subsequence converges almost surely to that same random variable. So this xnk has a further sub-subsequence, xnj say, such that xnj converges to c almost surely. Now take f that is continuous. Since xnj converges to c almost surely, fnxj converges to f of c almost surely, which is equivalent to saying fxnj minus fc converges to 0 almost surely. So since f is bounded, we could apply the dominated convergence theorem, and we could take from the almost sure convergence, throw away the measure 0 set, and apply the dominated convergence to establish convergence in L1. The expected value of f x and j minus f of c in absolute value converges to 0. But then we could use Minkowski's inequality, also known as the triangle inequality, to show that this implies the absolute value of e of fx and j minus e of fx converges to 0 for any continuous and bounded f. So we started with an arbitrary subsequence and we found a sub-subsequence that converged for any continuous bounded f, i.e. converges weakly to x. Therefore, for an arbitrary subsequence, we found a sub-subsequence that converges to x, which is equivalent to saying the original sequence converges to x weakly. We turn to the only if part, which means we assume that we have the weak convergence of xn to c. We got to show the convergence in probability. So let epsilon be greater than 0 and define the continuous bounded functions that are 0 except for between c minus epsilon and c plus epsilon. Between c minus epsilon and c, they ramp up linearly to 1, and then from c to c plus epsilon, they ramp down linearly. So this is clearly continuous and bounded by 1 in fact. We'll use this function and weak convergence to show we have convergence in probability. To show we have convergence in probability, we need to show that the probability of x minus c being greater than epsilon goes to 0. But that's equivalent to saying the probability that xn minus c in absolute value being less than epsilon goes to 1. And so the probability, though, that xn minus c in absolute value is less than or equal to epsilon, that's equal to the expected value that xn is in the indicator function on the open interval c minus epsilon to c plus epsilon. But that has to be greater than e of f epsilon of xn by monotonicity of integration. And now we know, since that's a continuous bounded function, f epsilon, that converges to e of f epsilon of c by the weak convergence. But f epsilon of c is 1 for every epsilon and is not random, so that expected value does nothing, and we're just left with epsilon of c, which is equal to 1, which is what we needed to show.
Dear U of A students, while Mike has supplied the content for these videos, there is significant unpaid effort that goes into producing these videos. The folks here at Step by Step Probability are family people with young children that no longer attend school due to the COVID shutdown. Instead of spending time with our families, we have made arrangements to continue producing these videos for you. In these uncertain times, it would be very encouraging to see your support through our donation button at the top of the website. Any amount is encouraging and appreciated. Please donate if you can. Thank you, and keep safe.